Welcome to the fifth presentation in the fourth webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We thank everyone for attending the webinar today. The webinar series has been an immense success, and the recordings of previous webinars continue to be viewed on YouTube and Bilibili. This is the fifth webinar of our fourth series, which we will continue to have monthly throughout the year. We intend to continue with a variety of speakers from industry, academia, and other research institutes, as well as PhD students and early career researchers. Announcements regarding the fourth series will be distributed through the IAS mailing list and the IAS Twitter feed. Today's webinar will be given by Dr. Hyungwoong Ahn at the University of Edinburgh in the United Kingdom. My name is Nicholas Wilkins at Svante Technologies Incorporated. Today's webinar will be moderated by Bhupesh Murugapan at the University of Alberta. We're required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member, if you are not already. Our dues are minimal, only $20 per year, but support the publication of our flagship journal, Adsorption, contribute to travel grants, and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS-supported materials, including our journal, as well as the adsorption database by Springer Materials. Anyone can follow the IAS on Twitter at @intadsots for future updates regarding IAS events, webinars, and information about scientific meetings. Please help us expand our YouTube channel by liking this video and subscribing. I'll now hand it over to Bhupesh, who will moderate the YouTube Q&A.
Thank you, Nick. It is my pleasure to welcome Dr. Hyungwoong Ahn to today's webinar session. Dr. Ahn received his PhD in chemical engineering at Yonsei University in South Korea in 2002. Afterwards, he did a postdoc with Professor Stefano Brandani at the University College London in 2003. In 2005, he was a senior research engineer in the South Korean Energy R&D Process Engineering Lab. In 2009, he became a senior lecturer in chemical engineering at the University of Edinburgh. In 2015, he won a KOFST Brain Pool Fellow with Dr. Chang-Ha Lee at Yonsei University in South Korea. His team specializes in the process design and analysis of PSA and TSA for gas separation and their experimental validation. They also study the use of process simulations to provide the solutions to decarbonize power and industrial plants. During the webinar, questions can be submitted to the speaker as comments on the YouTube live stream. Questions will be answered at the end of the presentation. With that, I welcome Dr. Hyungwoong Ahn again and pass over the presentation to him.
Hello. Thank you very much for introducing me to the audience, Nicholas and Bhupesh. My name is Hyungwoong Ahn. I'm one of the academics in the School of Engineering, University of Edinburgh. And the title of my talk is the equilibrium theory analysis of cyclic adsorption processes for gas separation. So if time permitted, I would like to explain how to apply the equilibrium theory to analysis of temperature swing adsorption and pressure swing adsorption. So I will start with the TSA first, because this is relating to my PhD topic. And then I would like to explain about my recent work on the pressure swing adsorption analysis using equilibrium theory. So during my PhD, the topic of my PhD was to design the temperature swing adsorption process for air drying. So I need to capture water vapor from the air using July 13X. So I need to do measuring the adsorption amount of the water vapor on the 13X, and also need to do the breakthrough experiment using the adsorption column here. So once the column is saturated with the water vapor, and then I did the thermal regeneration by flowing the hot nitrogen gas through the column. So the isotherm of water vapor on the 13X is type 1 isotherm in this concentration range. So which means I expect to see a sharp concentration front during the adsorption breakthrough, and in the desorption breakthrough, I expect to see a simple wave. So it's a proportionate concentration front. So when I did the adsorption breakthrough experiment using this column at the low water partial pressure in the gas, so in that case, concentration of the water vapor in the nitrogen was 0.53 mole per cubic meter. And the so it is equivalent to the 54% of the relative humidity. And once I start the breakthrough experiment, I increase the concentration of the water vapor at the inlet. And then after some time, the column is saturated with water vapor, and then the breakthrough started. So the water vapor break through the column, and then the water concentration at the outlet is increasing gradually up to the bead concentration. Then the column is completely saturated with the bead. Then we can terminate the adsorption breakthrough experiment. Now, I want to see the effect of the water vapor concentration on the breakthrough dynamics. So I increase the water vapor concentration in the bead to 0.86 mole per cubic meter, which is equivalent to 90% relative humidity. I start the experiment. Then what I expected is probably the breakthrough time probably shorter. So the water vapor will break through the column earlier than the breakthrough experiment with the low water vapor partial pressure. And the concentration will increase gradually up to the bead concentration. But what I saw in this experiment was, yes, the breakthrough time is earlier than the previous one, and then it started to increase, but at some point it did not reach the bead concentration. And I waited for the concentration at the outlet to reach the bead concentration, but it's never reached the bead concentration. So I was very surprised with this result, and I checked my experimental rig to check if there's a leak or if there is this problem with the analyzer. So I measured the water vapor concentration using hygrometer. So I replaced the hygrometer with a new one, but whenever I repeat this experiment, I obtain the same result. So there was no problem with this experiment. So actually, I couldn't find the answer to this problem. So I read the books by Ruspen or other experts in this area. And then I found this figure. So in the Loosband's book titled "The Principles of Adsorption and Adsorption Processes," published in 1984. If this is the type 2 isotherm, okay, so this type of isotherm, so there's the x-axis is the concentration, and then y-axis is the adsorption amount. Then the expected shape of the breakthrough curve is the shock front in the low concentration region, and then proportionate pattern front in the high concentration region. And that transition takes place at C prime here, and the C prime can be bound by drawing a straight line starting from 0 concentration to a isotherm. So that straight line should be on tangent to the isotherm. Then the straight line meet the isotherm, and the C prime can be bound. And that transition from the shock front to the simple wave take place at the C prime. So this is the exactly what I obtained from my experiment. And also in 1980, the Basmajian published a paper about the shape of the breakthrough curve given the shape of the isotherm. And this case is the type 2 isotherm. And then in case of type 2 isotherm, as you can see in the adsorption profile, there's a shock in the low concentration region, and then there's the simple wave of the in the high concentration region. In case of desorption, in the high concentration region, we expect to see a shock front, and then in the low concentration region, it must be a simple wave. So I extended the range of the concentration for the water adsorption isotherm measurement. And then, yes, it is clearly type 2 isotherm. And there's the capillary condensation take place near the saturation pressure of the water, given temperature. So if you look at the experimental result of the adsorption breakthrough, at the low water vapor partial pressure in the feed, this partial pressure of the water is within the favorable region of the isotherm, then it's a simple shock. But if you increase the water vapor concentration in the feed, then you may see a simple wave formed in the high concentration region, and in high water vapor partial pressure. This phenomena is very evident. So this is the one example of how to use the equilibrium theory, how to explain what happened in the experiment using the equilibrium theory. And also we can construct the adsorption and desorption breakthrough curve using equilibrium theory. So this is the method. And the theory starts from the mass and energy balance around the adsorption column. So the first equation is the mass balance. Obviously, we already applied the equilibrium theory to the mass balance equation. So in this equation, we have a beta I. The beta I is defined as the 1/1 plus 1 minus epsilon over epsilon times slope of the isotherm. And the second equation is the energy balance. Also, we apply the equilibrium theory. So dq over dt is converted to dq over d temperature T times the temperature over dt. Now we need to solve this mass balance equation here, and we cannot take the velocity out of this partial depressurization because the gas velocity changing with temperature. So we must keep the velocity inside the partial depressurization. To solve this equation, we need method of characteristics. So by applying the method characteristic, then we can solve this quasi-linear partial depressurization, and then we will obtain an equation similar to this. But in that equation, we apply the we assume the adsorbing component is dilute. So yeah, so this is the concentration characteristics for the adsorption system with the dilute heavy component. And by solving this energy balance, we obtain the temperature characteristic, WT. Okay? And you have to be careful about this equation. This equation is correct only if the adsorbing component is dilute. In case of a shock wave, instead of the slope of the isosome, we must use the secant of the isosome. The same for the temperature characteristics. And as I said, the gas velocity inside the column is not constant. And this fact is not considered well in previous publications. So you have to make sure that the gas velocity depends on the temperature and mole fraction as well. And for the concentration characteristic and the temperature characteristics, we apply the coherence rule to solve this equation. And then we can obtain the quadratic equation. From the quadratic equation, by solving that equation, we obtain the two value for the Tc over dt. And one dc over dt is positive and the other is negative. So we have a positive characteristics and negative characteristic. And sometimes the characteristic curve can be simple wave or the short wave. So I will explain this later. So this is the characteristic curve obtained from the solving the quadratic equation from the concentration characteristic and the temperature characteristic. So this is the system for the benzene, nitrogen, charcoal adiabatic system. And important thing is this TR. This TR is the watershed point where the selectivity reversal takes place, which means if temperature is less than this watershed point, positive characteristic approach this temperature axis asymptotically. So which means this positive characteristic is asymptotic to the temperature axis. But the negative characteristic simply intersect the temperature axis. But if the temperature is greater than the watershed point, then basically the opposite happens. So the positive characteristic intersect the temperature axis, and negative characteristic is asymptotic to temperature axis. So depending on these different trends, we can separate this graph into zone 1, 2, and 3. So how can we construct the breakthrough curve from this photograph plot? So in case of A to B, which means A is the initial point. The initial point means this column is already saturated with the adsorbate. So this column is initially contain adsorbate at the 10 millimole per liter. And then this column is regenerated by blowing the component, the state B. State B is the, there's no adsorbate, zero adsorbate. So it's the purge gas. Okay, so in the case, the rule to use is the starting from the initial point, and then we need to take the positive characteristic. So in this case, this one, and then from the final state, we need to take a negative characteristic. In this case, this one. So this positive characteristic and the negative characteristic from the final state intersect at point B, and point B is the plateau. So from this information, we can construct this breakthrough curve. So starting from the 10 millimole per liter, this is the point A, and then the concentration is decreased to the point B. In point B, the concentration is around 2 point something, so that one. And then it goes to 0. So that's the transition. And temperature is going down and then going up, like this. Okay. And the other case is the adsorption. So in that case, the point B is the initial point, and the point A is the final point. So the rule is the same. We always take the positive characteristic from the starting point. So in that case, the temperature is below the watershed point. So what we can say is the positive characteristic is asymptotic to temperature axis. So it's, we need to move along the temperature axis. Okay. And then point A is the final point. We take a negative characteristic. And then if you look at the characteristic, we can find out this is the shock wave is formed. So the shock characteristic is similar to the simple wave characteristic, but slightly different. And then this negative characteristic and the positive characteristic intersect at point F. That's the plateau. So in that case, starting point is B. So there's no adsorbate inside the column at the start. And then it goes to the plateau. The temperature is going up, but the concentration does not change. So it's still 0. And then the second transition from F to A, the concentration increased to 10, but the temperature is going down. Okay. So what happened is temperature profile is moving ahead of the concentration profile. We call this pure thermal wave. So if you do an experiment, then you can see that the column is very hot, but actually the adsorption takes place not in the hot section. Is the adsorption takes place is before the hot section. And in that case, the initial column temperature does not matter because which temperature, whatever temperature is the column is at initially, it will follow the path FA. So actually, the initial temperature does not matter. The watershed point is very important for thermal regeneration because we should not use the hot purge gas, the temperature of which is greater than the watershed point, which means, for example, B double prime is the initial point and H is the final point. So this is the feed. So the column is initially contains some feed, some adsorbate, and then this column is regenerated by blowing the hot gas H. And if you have a hot purge gas temperature greater than PR, so this is watershed point, then we need to take the negative characteristic from H. Then this negative characteristic will always follow this negative characteristic of the watershed point. So whatever temperature it is, as long as it is greater than the watershed point, it's always follow this negative characteristic. Okay. So even though you increase the temperature, the breakthrough curve is always follow the same, show the same dynamics. So let's go back to my PhD. So I did the adsorption breakthrough, the water vapor on the 13x, and this is the photograph plot. So this is the initial point. There's no water vapor inside the column. And then we started feeding the water vapor mixture at the 0.523 mole per cubic meter at 293 Kelvin. So the rule is the same. The starting point, we take the positive characteristic, and then we take the negative characteristic from the final state, and the two characteristics intersect each other at this point. Okay, so the symbols indicate the experimental result of the water breakthrough, and the dashed point is the equilibrium theory result. So as you can see, there is a first transition where only temperature change. There is no concentration change in the first transition, which means the pure thermal wave is formed. There's no concentration change, but temperature is going up by first transition. And then that's the plateau temperature. And then in the second transition, the temperature is going down, but the concentration is going up from 0 to 0.523 mole per cubic meter. And the solid line is the numerical simulation result. So you can see the equilibrium theory shows the shock wave in the first and second transition, but in the numerical simulation shows the bit of the slope because of the mass transport resistance. And for the desorption, I use the three different temperatures gas. So 423, 473, and 523. And if you increase the temperature of the purge gas, what you can see is the low of the concentration increased, and the regeneration time is shortened. And the question is, the equilibrium theory can estimate this trend, okay? Can predict this trend. So this is again the photograph plot for the water desorption. So I is the initial point. So column is saturated with the water vapor at this condition. And the F, three different F means three different temperature of the hot nitrogen gas for the thermal regeneration. And if you increase the regeneration gas temperature, as you can see, the plateau concentration is increased, which means the low of the concentration during the desorption breakthrough become larger. And also important thing is this choice of the hot purge gas temperature must be less than watershed point, because if you choose a temperature for the hot purge gas greater than watershed point, there's no benefit from increasing temperature. So that's the breakthrough curve of the desorption case. And what is interesting to me is the in case of the 423 Kelvin, it's the simple wave. Okay? The dynamics of the desorption breakthrough is the simple wave, but if you increase the temperature, it's initially simple wave, and then it has shock, and then simple wave. And if you increase the temperature of the hot purge gas, then the portion of the shock wave is increased, which means the desorption becomes more efficient. It can be finished much earlier. Okay? So that's the what I found. So depending on the level of the desorption. So for example, in the at the outlet of the column, the the water vapor mole fraction decrease. And if you don't need a very vigorous regeneration, then probably the temperature of the purge gas doesn't matter, because the temperature, I mean, the time required for the regeneration is more or less the same or very similar to each other. But if you really, I mean, if you have to regenerate the column more rigorously or thoroughly, like a dew point of the minus 20, 30, then if you have a very low temperature of the hot purge gas, it takes a long time. So in that case, you really need very hot purge gas for the regeneration to make to regenerate the column as quickly as possible. So this is the temperature swing adsorption part, and now is the PSA analysis by equilibrium theory. And I presume that you already know how to derive the basic equation for the equilibrium theory to estimate to analyze the PSA system. So I will skip this part. And the important thing is for the PSA system is to estimate the product recovery of the PSA system. So, I mean, the PSA product purity has to be always very high, like 99 or 99.9. But the product recovery can be changed depending on the design of the PSA process or operating condition of the PSA process. So in this example, I would like to show how to estimate the product recovery of the PSA system using equilibrium theory. So without doing any numerical simulation or experiment. So that example comes from the again, the Roosevelt book. So that book. So probably I have to skip many parts to explain this concept very quickly. So if you're interested in the theory, please refer to this book. So that's the important equation to use to estimate the product recovery of the PSA system. So this is the equation we can derive from the mass balance equation using method of a characteristic for the simple wave. And if we have a shock wave, then the shock wave propagation velocity can be estimated by this equation. And also we need to estimate the velocity. Okay? So if the constant pressure steps, the velocity of the 2 points, so two position 1 and 2 are related with this equation. If the isosums are linear for both heavy and light component, that equation can be simplified to this equation. So in that case, the beta is constant, so we can easily integrate this equation. If the both isosums are linear, then we get this equation. And also if the equilibrium constant is very high, then beta becomes 0, then can be further simplified into 1 minus YA1 over 1 minus YA2. This is for the simple wave. And if the shock wave, then we need this equation to find out the velocity. So if you know the feed velocity, then you can find the other velocity. I mean, the velocity at other position. So the U1 and U2 is the velocity, two velocity around the shock. So you can find the velocity from this equation. And also we also need the equation to estimate the velocity when the pressure is changing, like the blowdown pressurization. We need to use this equation. The derivation of these equations are require another 1 hour for lecture. So now we are going to estimate the product recovery of the PSA system. And in the Roos-Bensbrook, there are two cases. So one is the 4-step PSA process with the feed pressurization, and the other case is the 4-step PSA with product pressurization. And obviously, the product pressurization case is simpler because we don't have to consider the adsorption taking place during the pressurization. So we are going. I'm going to explain the theory based on the 4-step PSA with product pressurization. We need a number of assumptions to make the equation simple. So we are going to estimate the product recovery of a 4-step PSA with binary gas mixture gas. And this is, obviously we have to consider a limiting case to make the equation simple. So the heavy component isosome is nonlinear. Can be nonlinear, but light component isosome is linear. And two isosomes are uncoupled, which means one component adsorption will not affect the adsorption amount of the other component. So completely separated. And the column is completely regenerated during the purge step. And the purge step will end the moment the column is completely regenerated. Actually, this is quite bold because in practice the column will not be completely regenerated, because if you regenerate the column completely, then the product recovery sometimes is very low. But this is the assumption to make the equation simple. And all the assumption involved with the equilibrium theory hold, and the system is isosomal. So this is the characteristics on the ZT plane for the 4-step PSA system with the complete regeneration. Okay. So there's a 4 steps: the pressurization, bead, blowdown, and purge. And the y-axis is axial position, and this is the time or pressure. So if it's there's no, this tight section, the clean section means there's no heavy component because the column is completely regenerated during the purge step. There's no heavy component inside the column at the start of the pressurization, so there is no heavy component because column is pressurized with the light product. And then during the bead step, we expect to see a shock front to be formed, which means the shock is propagate from the bead end to product end. Once the column is completely saturated with bead, then we have to stop the bead step, and then we decrease the pressure during the blowdown step. Okay. And then the column is regenerated gradually by feeding the light component. So that's the situation inside the column during over the one cycle. So how can we estimate the product recovery? So that is the equation. Okay. So RB is the product recovery. So denominator here is the light component, total moles of the light component fed to the column during the bead step. And then in the numerator, the first term is the total moles of the light component leaving the column during the bead step. And the second term is the moles of the light component used for the pressurization. And the third term in the numerator is the total moles of the light component used in the purge step. Okay. So that is the simple mass balance over the cycle, and we can obtain the product recovery, RB. Now, what we need to do is to find out the bit step time and the purge step time. So the bit step time is the TF here, and then bit step time is estimated by the column length L divided by the speed of the shock wave. That speed of the shock wave propagating from the feed end to product end. And this one is from this governing equation here. Here, theta A times, in the case, we assume the clean bed, so YA2, YA2 0, so these terms cancel out, and YA1, YA1 cancel out, so simply becomes theta A times U1, so that one. And the purge steps, as we expect to see the simple wave to be formed during the purge step, so we need to identify which simple wave is the slowest in the speed during the purge step, and obviously the speed is inversely proportional to the slope of the isosome, and the slope of isosome is the largest at the concentration equal to 0. So we have to choose that concentration to estimate the speed of the simple wave. So that is the speed of the simple wave. So L over the speed is the time. So we can find the total moles of the gas fed to the column during the 2 steps. And also, we need to find out the total moles of the pure light component produced during the feed step. Okay, so the time for the feed step is the same as before, but instead of QIN, we need to find out what is the Q out. Q out is the velocity of the gas at the outlet. Okay, it's related to the gas velocity at the outlet, and the gas velocity at the outlet can be found from the governing equation. Okay, again, that equation. So simply use that equation, then we can find the total moles of the pure light product withdrawn during the feed step. And lastly, we need to find out total moles of the light component consumed for the pressurization step. So that is the pressure changing step. So we have to integrate the flow rate over the pressure range from PL, low pressure, to pH, high pressure. Okay. Then we can find out the total moles of the light component used for pressurization. Now we found all the expression for the 4 terms in the product recovery equation. Simply substitute the expression for the terms and then rearrange the equation, and you should get this equation, the second equation on the slide. And in this equation, we have a theta A over beta A0, and this ratio reduced to unity 1 if the isosome of the component A is also linear. So both isosomes are linear, then theta A is the same as beta A0. Then we can simply simplify this second equation further to third equation. The message I want to deliver in the slide is the information required to compute the PSA recovery is isotherm, temperature, and 2 pressures, high pressure and low pressure, adsorption and desorption pressure, and bed void fractions, epsilon, and feed composition. Then you can estimate the product recovery. You don't need the flow rate, you don't need column dimension, you don't need the step time, cycle time. Simply, you don't need those information. And Yes, so the model I explained is developed by the Kaiser and Knebel. Yes, so light component is linear and heavy component is non-dilute and non-linear. And the simpler models involving the additional assumptions had also been developed before this Kaiser-Knebel model, the Shanderdon-Mitchell model or Hyungwoong Knebel here. You can see the different simplifications applied to the model to derive the equation. So if you look at the Loosban's book, you can find this table, and he computed the recovery based on the 4 different models to estimate the recovery from the 4-step PSA with product pressurization. For the 2 different systems, one is nitrogen helium. So nitrogen is heavy component, helium is light component. And for nitrogen oxygen, nitrogen is heavy component and oxygen is light component. So in my course, I lecture this contents in my course, and then I ask students to compute this recovery to reproduce this table. So you can do that as well. So obviously, you can estimate the recovery from the 4-step PSA with complete regeneration, but this complete regeneration is not realistic. And to maximize the product recovery, you have to, you should not regenerate the column completely. And also, if you want to if you want to improve the recovery of the product, then you have to add pressure equalization step or co-current depressurization step. So what I did in this research is to find out the effect of number of pressure equalization step on the product recovery. So, for example, in case of hydrogen pressure swing adsorption system, hydrogen purity must be very high, like 99.9 or 4959, but hydrogen recovery of the industrial SMR hydrogen plant is around 89%. And that hydrogen product recovery can be different depending on the design of the process. So usually having more pressure equalization step, so more than one pressure equalization step, can improve the product recovery. And if you want to accommodate more pressure equalization step, you need more columns. So if you increase the, for example, the number of pressure equalization step, you can increase the product recovery from 84, 90 to 93%. Okay. So my question was the PSA product recovery would always increase with more pressure equalization steps added to the cycle. So I did a literature review on this subject, and yes, if you increase the number of the pressure equalization step, then you can increase the product recovery. And then I simply chose this Walden and Zucker's work for an example. So I tried to study on this. So Chiang did the fantastic work in the past. He developed a very robust equilibrium theory model for the pressure swing adsorption with pressure equalization and co-current depressurization step. So what I did, simply use this model to analyze the PSA system. And in that model, the isosystem has to be linear for both components, and we can consider backfill or feed pressurization. Okay, we can estimate the light product recovery and the throughput using that model. There are 3 different indexes for the extent of purging. So minimum, critical, and optimum extent of purging. And you probably use the one of the critical and optimum extent of purging. depending on the values. And that's the equation to estimate the product recovery. So simply what we need to do is to find the X, extent of purging. We are going to use critical or optimum. It depends on the value. Skip. So this is the isosome of the CH4 and hydrogen isosome. Yes, almost linear, but the CH4 isosome is non-linear. So to use the Chiang's model, I use the second of the isosome, given the beta composition of the CH4. And then this is the result for the 4-step and the 5-step with the co-current depressurization. So this is the 4-step PSA with product pressurization, hydrogen recovery, okay, depending on the CH4 mole pressure in the feed. And then by having the co-current depressurization step, we can increase the hydrogen recovery like this, okay? And then this is the effect of the number of the pressure equation step. So if you have, depending on the mole pressure in the feed, the optimum number of the pressure equation step to maximize the hydrogen recovery can be different. Okay? So in the very low CH4 concentration and mole fraction in the feed, the optimum number of the pressure equation step is very high, more than 3. But if the CH4 mole fraction is very high, like 0.9, 0.8, then only one pressure equalization step is enough. If you have more than one pressure equalization step, basically you will worsen the hydrogen recovery. So you do not have to have more than one the pressure equalization step. Okay. So we can estimate the effect of the pressure on the product recovery using the equilibrium theory, and also the result from the equilibrium theory was compared with the numerical simulation result from the Waldron and Zucker paper, and the equilibrium theory result, was in good agreement with the numerical simulation result at the qualitative level. And also the way of the pressurization can be feed pressurization or product pressurization. And the Knabel et al. Did a numerical simulation study with the optimization. And they found the product pressurization would be better than feed pressurization in terms of the hydrogen recovery. And basically, equilibrium theory gives you the same message. So the product pressurization method be better than feed pressurization in terms of the light component product recovery. So the conclusion is the equilibrium theory is simply the mass balance around the column. So if you are very good in the mass balance, and then it's very easy to understand how to use the equilibrium theory in analyzing the TSA or PSA. So yeah, most of the example I showed in this presentation from the Roosevelt book, and where you can find the nice explanation about the adiabatic columns breakthrough for adsorption and disruption. And also I explained the how to estimate the product recovery from the 4-step PSA with product pressurization, where the column is completely regenerated. And the important message I want to deliver is the equilibrium theory can be utilized to optimize a PSA system for maximizing the product recovery or maximizing the bad productivity without numerical simulation. And currently I'm working on the I'm working to optimize the CO2 capture vacuum swing adsorption process using equilibrium theory. So if I given another chance to present the webinar, then I would like to explain this. And thank you very much for listening to me.
Perfect. Thanks a lot, Dr. Hahn, for your presentation. It was really interesting to study how equilibrium theory can be used to predict the process performance for the cyclic adsorption process. While we are waiting for questions on YouTube, I have a couple of questions from both Nick and I. Do you think there are any papers that could be a good introduction to the derivations of equilibrium theory, or are there any books that can talk about the introduction to equilibrium theory, especially for someone who's new to it?
So my recommendation is to read this book. This book is anyway, there are two books authored by the Luspen, and this is one of the book. It's very useful for newcomer in this area. So yeah, I recommend reading this book. And starting from this book cited a number of papers, and yeah, so once you start reading this book, then you need more information about this subject, and then read the original paper about the information. And yeah, that's what I did.
Okay.
Also, ask me a question.
Yeah. So we also compared the numerical solutions and that of equilibrium theory, the profiles and histories. Do you have any comments on the comparison of the computational time? Can we say that the equilibrium theory is much faster than the numerical solution?
Equilibrium theory is just the instant.
Okay.
Yeah. I'm solving the model using the MassCat and MassCat less than 1 minute.
Okay, that makes sense. And do you think equilibrium theory can also be extended to flexible morphs? We see a lot of them these days. Let's say we have a breakthrough with a flexible morph. Do you think equilibrium theory can still predict it? Do we need to add some extra term? Is it going to be very difficult? Or
so what do you mean by the flexible? So
some morphs actually show flexibility upon CO2 adsorption or something, and which would probably cause a change in their breakthrough profile. So do we still think equilibrium theory can predict it?
Yes, I mean, the information we need is the isotherm, because we neglect the effect of the mass transfer resistance or axial dispersion in this model. So yes, not this one. 1 second. So this is the information we need to estimate the performance. And then if you change the adsorbent, then you will get the new isotherm, right? And yeah, given the isotherm, probably you need to optimize the adsorption pressure or desorption pressure to maximize the performance of the PSA process. So basically, I mean, I'm currently using the equilibrium theory model to estimate the CO2 product recovery from the PSA system. So it can be utilized for the light component. The PSA system can also accommodate the lightly flux, heavily flux, or light product pressurization, heavy product pressurization, lean step. So any steps can be accommodated. And then it's very flexible once you understand how it works. So
okay, and a good follow-up to that is, can we also apply the equilibrium theory, the same analysis that you have shown here on this slide, to, let's say, an extract cycle? It should be straightforward, is it?
I beg your pardon, sorry.
Can we extend the equilibrium theory analysis to an extract cycle as well?
Extract the cycle?
Or the heavy product cycle, in other words?
Yes. So one of the recent, I mean, also you can find the information from the Luspen's book. There's an example of the PSA system containing the heavy density step. he explained how to analyze this cycle with habit step using the equilibrium theory. And I use that equilibrium theory in the book to estimate the performance of the PSA system to capture CO2. And then I published the paper a few years ago. So yes, it's possible. It's not that difficult. So the important thing is the how much we have to regenerate the column during the purge step. That's the important parameters. So you know, if you regenerate the column completely, then the product recovery is become rubbish. So you have to optimize the extent of purging during the purge step to maximize the product recovery. And also you have to consider the during the adsorption step, we have to make sure that the shock front is to be formed along the column, which is relating to the critical extent of purging. Otherwise, during the we cannot apply the equilibrium theory. So
okay. Okay, and we have a question from YouTube as well. The question is the effect you've seen about the number of equalization steps. Can it be extended to equalization via tanks, or is it only valid for bed-to-bed pressure equalization?
You mean this? Bed tank, you know, bed tank equalization, right?
Yeah, can it be extended?
Yeah. So I think the Professor Jim Litter's groups did fantastic work on this subject. So they work involving the increasing number of pressure equalizer step without having to increase the number of bed by having a buffer tank. So yes, and I think it's possible, and there's some paper already published from the Professor Jim Litter's groups.
Okay, and we have one more question on YouTube. Can equilibrium theory work when you take kinetics into account as well?
That's the tricky question. Yes, but limited. So there is also some example in Luspan's book where the equilibrium theory was utilized with the mass transfer resistance also considered, and then in that case, if I remember correctly, the isotherm has to be very simple, like irreversible isotherm. Then there's a way to increase. There's a way to include the effect of the mass transfer resistance. Also, there's a model developed by the Hyungwoong Ahn and the in the book. They also consider the axial dispersion effect included in the equilibrium theory. So probably equilibrium theory can be applied to all the cases, including for the mass transfer resistance effect. But in the very limited cases, it is possible.
Okay. And we have one more interesting question on YouTube regarding the low concentration of carbon dioxide in the DAC processes. What are the challenges in dynamic column breakthrough and equilibrium tests? This is the question from Kian Karimi.
In the low concentration of the CO2?
Yeah. Let's say, for example, the DAC process, what could be the challenge in doing like an equilibrium theory analysis?
Can you describe what is DAC process?
The direct air capture at 400 ppm.
Okay, direct air capture. Okay. It probably I'm not the expert in this area, but the challenge is the probably with just one stage of the adsorption process, it may be challenging to increase the CO2 concentration from the 400 ppm to over 95%. So I think the equilibrium theory can be useful in identify the challenging on the direct air capture using adsorption. But the problem is one of the example of the challenge of the adsorption process is the desorption pressure has to be very, very low to have a positive product recovery. What I'm saying is, if you want to increase the CO2 purity from 400 ppm to 100% at one stage, then you need very low desorption pressure to achieve this this target. So probably so we have to develop the process sequence, step sequence of a cycle, optimize this step sequence, and also we have to optimize the operating condition as well.
Okay, and probably we could think about a temperature swing there, right?
Yes.
For a very low composition.
Yes,
okay,
that's a good idea. Yes.
Okay, yeah, makes sense. We don't have any other questions on YouTube. Thanks a lot, Dr. Ahn, for answering all of our questions. It was really interesting.
Thank you very much.
I'll hand over the control to Nick Wilkins.
Thank you, Dr. Ahn, for your presentation, Equilibrium Theory Analysis of Cyclic Adsorption Processes for Gas Separation. We also thank all of our attendees for joining this webinar and hope that was both educational and enjoyable. An edited version of this webinar will be posted to the IAS YouTube channel and Bilibili, along with an announcement on the IAS Twitter feed. The hope here is that the work discussed today will be a useful resource for the adsorption science community in the future. The next confirmed IAS webinar will be given by Carlos Grande on July 12th at 2 p.m. UTC. Announcements regarding the next webinar and other IAS online events will be posted on our Twitter feed and through the IAS mailing list. With that, we thank you for joining us, and we hope that you will join us again soon.